intermediate value theorem, intermediate means in between, okay? So it says basically that if you've got these numbers a and b, and then you plug them in, f of a and f of b, if you get the opposite sign, like one of them's positive and one of them's negative, then there exists at least one real zero between them, okay? So if you read through that, I think it's confusing, but if you look at it, it makes a lot of sense. Use synthetic division in a graph to show that this polynomial has a real zero between 1 and 2. So we're going to do synthetic on these two numbers. Synthetic division with a 1. Add down and multiply, add down and multiply, add down and multiply, add down. What that means right there is f of 1 equals 2. When I plug in 1, I get 2. So now let's do synthetic division on the number 2. Add down and multiply, add down and multiply, add down and multiply, add down, negative 3. And what that means is f of 2 equals negative 3. Okay? So that's enough really to answer this intermediate value theorem, but let's look at a graph. F of 1 equals 2 means there's a point right there. Okay, f of 1 equals 2. That's like the point 1 comma 2. And f of 2 equals negative 3 means there's a point right there. F of 2 equals negative 3, or you think about the point 2 comma negative 3. So f of x is some function. And I don't know exactly what this function looks like. It doesn't really matter. But if you connect the dots here, the function, the function has to look like that at least at some point if you zoom in. And so it crosses the axis right there, but that's a 0. And so all this says, all the intermediate value theorem says, is that if you plug in a number and get a positive value, and you plug in a different number and get a negative value, that means we're up here in positive and down here and negative. There has to be a 0 in between. And that makes perfect sense. So you can summarize and say something like, since f of 1 is positive and f of 2 is negative, there must be a 0 between 1 and 2. I think the boundedness theorem is a little bit harder to understand, okay? We can read through all of this, and we're not going to understand it until we actually do an example, okay? So notice there are two cases, case A and case B, but it has something to do with synthetic division. So we're definitely going to do synthetic division. In this case, example 6, we're going to do synthetic division on this 1. Now notice you're missing your x cubed term, so don't forget to put a 0 in there. 1x to the 4th, 0x to the 3rd, 5x squared, 3x minus 7. So synthetic, we're just going to add down and multiply, add down and multiply, add down and multiply, add down and multiply, add down. Okay. Now let's go back and read what it says. Case A says, if C is greater than 0, well, this was my number C, okay? If this number is greater than 0, and all numbers in the bottom row are non-negative. So see how we've got a positive, 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 positive. So in other words, if this number is positive and all the numbers in the bottom row are positive, then here's our conclusion. We can conclude f of x has no 0 greater than c, which was 1. I know that's kind of hard to understand, but I think the example makes it a little bit more clear. Case B is going to, or part B is going to show case B. So again, let's just look at synthetic division. Do synthetic division with this negative 2. You have 1, 0, 5, 3, negative 7. Add down is 1 and multiply. Add down is negative 2 and multiply. Add down is 9. Multiply negative 18. Add down negative 15. Multiply is 30. Add down 23. Okay? So, check it out. It says if c is less than 0, that's less than 0. Or in other words, negative. And the numbers in the bottom row alternate in sign. So see how they go positive, negative, positive, negative, positive. Okay, that's what they're talking about. The bottom row alternates in sign. Plus, minus, plus, minus, plus. Then here's your conclusion. F of x has no 0 less than c. So we could conclude that f of x has no 0 less than negative 2. I know that's difficult to understand. Okay. Example 7 says approximate the real zeros of this thing. Approximate. Yes, question?
So is it like setting like a range for it?
Kind of, yeah. It's setting a range because we know that there's no 0 that's greater than 1, but we know there's no 0 that's less than negative 2. So if you were going to graph it, then whatever it does, it's an x to the 4th. So that's a positive even. So I know it's going to do something like, something like that. Okay, it kind of sets a range for where this thing crosses that axis. Okay, I'm not even sure if that's exactly what it looks like, but it's fairly close. All right, it's going to be in between positive 1 and negative 2. Good question. If I'm going to approximate zeros, that's telling me to use a calculator. So I think the best thing to do is go to Desmos. You can use your graphing calculator if you want, but I feel like Desmos is a better grapher. So we want to graph negative x to the 3rd plus 5x squared plus 3x minus 7. All right, so that's kind of what it looks like. You see a negative odd function, but we want the zeros. So you just click here. Did I mess something up? Oh, how did I do that? I don't know what I was. Oh, I was looking at number 6. Sorry. Minus 8x squared plus 4x plus 10. I was doing number 6. This is number 7. Okay. Number 7. Here we go. Like this. And you can find your zeros right there. Negative 8.336, negative 0.94, and 1.276. And again, that would be good for graphing, I guess, for solving. But honestly, if you can use Desmos to find the zeros, then why wouldn't you be able to use Desmos to graph it? So that'd probably be better just for graphing.
So like the numbers are close in the calculator, but they're not like stacking on. Would those close numbers work?
Well, it's probably not close enough to like if you're typing it into Math Excel.
Yeah.
There is a function on your graphing calculator to find the zero. Try like a second math or a second graph. I can't remember. I'll have to show you later. But there is one that'll get you a little bit closer and a better answer. But I still think Desmos is faster. Okay, I'll show you that later. Problem 8, last one. Use a regression calculator to find models for the data in this table. Okay, we've got 3 different questions here, and the problem is, or the question is usually something like, what's the equation? What equation fits these data? And so sometimes it's a line, or sometimes it's a quadratic, or sometimes it's a cubic, and at this point we don't really know. Okay, and so they're taking me through and having me figure out if it's a quadratic or a cubic or a quartic. That means x to the 4th. Okay, so at this point I don't really know what kind of a model it is. Is it quadratic? Is it cubic? Is it quartic? What do these data represent? So if you go to the math sites on Goldadder, you'll see there are a couple of regression calculators. Linear regression is good, but it only does a line. Quadratic regression is good, but it only does quadratic. Same thing for exponential. If you go to polynomial regression, that's the one we want. Because this will let me do different powers. It'll let me do a quadratic or a cubic or whatever. It took me a second to figure out how to enter the numbers in, but what you do here is you enter your x and y numbers without a comma, okay? So go back and look at your numbers. We're going to say 1990 is year 0. So 2, 5, 8, and this would be 10 years after start, 14, and 18, and 22, okay? I think that'll just be easier for us to zero it out. So that way our axis starts at 0. So look at these numbers, and that's what we're going to enter into this regression calculator. And here's how we're going to do it. We're going to go 0 space 127, enter for the second line. And 2 space 204, enter. 5 space 829, 8 space 3765, 10 space 5290, 14 space 14106, 18 space 28464, and 22 space 44351. Okay, now you want to select polynomial degree. Degree 2 is quadratic, and then we hit calculate. So it gives us some stuff, but the 2 numbers we want, I guess we want this equation right here. That's the model, and we want this r squared number. This r squared number kind of tells us how good of a model it is. So let's do the r squared number first. Notice it says times 10 to the negative 1. I know that's a little bit confusing, but times 10 to the negative 1 is going to move this decimal place 1, bless you, 1 over. So I would, instead of saying all of this, I would say 0.9983. All right, 0.9983, we'll just do 4 decimals. So 0.9983. That's the r squared value, and that's how good of a measure it is. The closer to 1, the better it is. And then the model is this equation right here, 121 point, let's just do 2 decimal places, 121.11 x squared and then it was minus 676.41x plus 700.26. Okay, now we've already got all the numbers typed in, so all we have to do here is change it to degree 3 and we can do a cubic. So hit calculate and new numbers come up. Notice this r square value times 10 to the negative 1st moves that decimal over, so 0.9986. 0.9986 is a little bit better model. When you go back and look at that equation, 8.7, it's times 10 to the negative 1st. So notice that you're going to have to move that decimal over. So Let's call it 0.87. Okay, now we need the quartic, so let's just change this to a degree 4. And this r squared value is going to be 0.9994. All right, so even better. And the model, again, there's a times 10 to the negative first, so we have to move the decimal again. So negative 0.31. So there, we've got 3 different models for these data, okay? Is it quadratic? Is it cubic? Is it quartic? Part D says which of the models is best. Well, you look at the r squared value, and the closer the r squared value is to 1, the better the model is. So I would say the quartic is the best model. These data would most closely model an x to the 4th equation, because that r squared value is closest to 1.